I welcome you to Statistical Inference class. And today, under the Statistical Inference, we'll be looking at sampling and sampling distribution. In Statistical Inference, it is important for us to familiar ourselves with some certain definitions. As you know, before we can make a statistical inference, we must know the population we are dealing with. There must be a population and there must be a sample. And at the same time, there must be a random variable we are dealing with. So, a statistical inference are inference generated about a population of interest. So what do you mean by population? Population simply implies the set or collections of all possible identical observations. And for instance, if you are interested in or carrying a study on staff job satisfaction of a particular company, so the set population would be what? Would be all the staffs of that said company. And the same thing applicable to a sample size. So sample is a part, or we call a subset of population. So a sample is a drawn set from a population. So if that is clear, for you to have a sample, there must be a size, and that's what we call sample size. That's what we call random sample size itself. So a random sample size in statistics refers to a sample that is chosen in such a way that ensures all the elements has equal chance of being chosen. So that means a random sample size. Good. An important thing to know in statistical inference is also parameters. A parameter is said to describe a population, a given population, while the statistics is said to be what? To be a function of the sample you drawn from the populations. So if that is known, and also an important part of it is probability distribution, and it's said to be what? To be once you know your statistics, so the probability of that statistic is known as sampling distribution. So what I said earlier is just this. When we say population and samples is a set of all items of an individual of interest. So you could see an example here: voters or likely voters in the next election is an example, while the sample is a subset of that population. So if we draw a size of 10 or 20 from the population example, you said to have a sample. Another example is a population. A population is a set of alphabet from A to Z. You see, you can draw as many samples as you can. If we're looking at sample of vowel letters, you can draw it. Sample of consonant letters, you can draw it, and so on and so forth. So the important thing is that what you should know, that when we're dealing with population, we refer to parameter, and when we're dealing with sample, we refer to statistic. So One important features of sampling is sample mean. Sample mean, and the sample mean is a statistic of a sample. Remember what a statistic is. So statistic is a function of a sample. So here we have a sample mean. So from the set, assume we have a set of x's of size n, and it's drawn from a populations of mean of mu and variance of sigma square. So the mean there is the parameter, the mu there is parameter, while the sigma square, which is our variance, also the parameter of a population. So we said the statistic mean is defined as this. So one important features of this sample mean is that when you take the expectation of your sample mean would give us the population mu. Hence we said is an unbiased estimator, and that's what refers to as unbiased estimator. So if you expand this A, would give you that. B, so if you expand this expectation of x bar, open this bracket and do the mathematics here to give us the mu. So it's an unbiased estimator. Second one is the variance of the sample mean. So the variance of the sample mean, that means how the sample mean deviate, how the sample mean, the variance of the sample mean, and given that your x's are independent. Remember, independent means that what x2 does not depend on the occurrence of x1, while x3 does not depend on the occurrence of what, of x2, and so on. So when you have that, when you take the variance of that, would give us, expand the math, do the mathematics, will give us 1 over n sigma square. And the last part of it is when your x's are not independent, that means x2 depend on x1, x3 depend on x2, and so on. So it involves us adding what we call correction factor, and correction factor is defined as what, as population size minus sample size over population minus 1, and this is what we refer to as correction factor. And it will interest you to know that as n gets larger, if your n is large relatively to n, then all this would be 1 tends to 1, hence it will still be what, give us 1 over n sigma square. So thus the variance of sample mean is decreasing function of the sample size from here. So let's look at the variance, the sample variance itself. Let's look at it. Would the expectation of the sample variance give us the population variance? Let's look at it, and that is what is shown here. From the same random sampling size, and when your sample variance is defined as this x squared equals to 1 over n minus 1, this all square, when you do the mathematics, when you take the expectation, would be what, would give us sigma square. So the expression of your sample mean, the expression of your sample variance is an unbiased estimator. It's shown to be what, to be an unbiased estimator. That means it will give us the population parameter back. So let's take a scenario when we're sampling from a normal population. Sampling from a normal population of size n with same property of mean to be mu and variance to be sigma square. Then we know that what, as shown earlier, expectation of your sample mean will give us mu, population mean, and the variance of the sample mean will give us this. So if we further specify the population distribution as being normal, then we can write x to be what? X bar, that means the statistics, to be from a normal distribution of mu and 1/n sigma square. Do you understand? Thank you. The next is the standardization of sample mean. So we want to standardize sample mean, and you should know from the generic formula of standardization is what? Random variable minus mean of the random variable divided by the standard deviation of the random variable. So we know that what we've shown that sample mean from a normal distribution tends to what? To be normal distribution of mean of mu and variance of 1/n sigma square. So when you substitute that into the formula, generic formula of z, that is standard to want to standardize the sample mean, it will give us x bar minus 1 mu minus mu over sigma square root n. When you substitute this into this, we give you this. So some properties of sampling distribution properties. As n, what do we notice? We want to have what happens when your n increases? What happens is what? The standard deviation decreases. So that's what it implies. And for every large sample size, you see it tends towards to be normal. It tends to be normal. That's what it simply implies. When you keep sampling, if your n increases, the chances of it what to become normal. So that's what this chart is all about. And when you have a small sample size, what do you mean? The curve tends to be flat. It tends to be flat. So let's look at an example of standardizing for sample mean. We have an example of a length of individual machine parts coming off a production line at Morton Metal Works. We said the distribution are normally with mu of 30 centimeters and standard deviations of 0.1 centimeter. So an inspector just took a sample of 4 and find the mean to be 29.875. So the question is, what is the probability of getting a sample mean that is lower if the process still produces part at that same population mean of 30? So with divine this, we'll know that the x is here. Our sample size is from what? A normal distribution. So in normal distribution, that means the mu of the normal of this distribution is what? Is 30, while the standard deviation is what? Is 0.1. And the relationship between standard deviation and variance is that what? Variance is what? Is a square of standard deviation. So when you do the mathematics, you tend to have x to be normally distributed with the following property. So our interest is to estimate the mean to be less than 29.875. So when you substitute that into your standardized formula of z, you have this. So it will give us That's mathematics. And when you use the statistical table of Z, you will find out that what the probability of this standardized of minus 2.50 will give us 0.0062. Let's then now consider sampling from non-normal distribution. And we have an example of four individuals here that constitute a population, and we are interested in their ages. So their age here are the random variable x. So the population size is 4. So we're interested in their ages. If we let's calculate the population itself, population parameter. So the population parameter of that, when you do the mathematics of mean of 4 individuals with age of 18, 20, 22, and 24. When you take the mean, that means population mean, it will give us 21. And their variance, or say standard deviation, when you do the mathematics, will give us 2.236. And remember, they are non-normal distribution. They come from non-normal distribution. So if the chances of them, since we have 4 individuals in the population, so and we're dealing with random sampling, remember, random sample size, definitely they all have equal numbers of chances of being selected. Hence, the probability of them being selected would be 0.25 being equal. And that form what we call uniform distribution. Let's consider sampling size of 2. So we're interested in selecting 2 at a time, and remember, with replacement. What are the ways of selecting sample size 2? And that is what you have here. You can pick 18 and 18. You can pick 18 and 20, 18 and 22, 18 and 24. You can pick 2018, 2020, 2022, 2024, and so on to 24. So therefore, we have how many ways? We have 16 possible ways of sampling, of sample size, sampling in when n is 2. Give us 16 samples. So when you take the mean of each of your sample now, we'll take the mean of each of the sample would give us the 16 sample means, 18, 19. So that means each of these sample divided by 2 will give us this. And let's see the distribution of the sample means. So when you look at the distribution of the sample mean, that means 18. How many 18 do you have here? 18 is 1. 18 divided by 16 will give us this, and the probability is plotted in red here. So you could see that when you do a random sampling of your sample size, instead of, remember, we started from uniform distribution for your population. For this population, each of the S's has equal chances of being selected. But when it comes to random sampling, what do you intend to have? It is no longer a uniform distribution because of your sampling, and hence you will see there is a tendency of having a normal curve. Look at the plot in red. See that it tends to be what? To be normal. Based on the probability of occurrence of your mean. You see mean 18, 1 over 16. 19 will give you 2 over 16. 20 will give you 3 over 16. And 21 will give us 4 over 16. And you see that, and down, so it's down to the last 21, 24, which is 1 over 16. So it tends to be normal. And that leads us to central limit theorem. It's important. Once we have a non-normal distribution, we can apply a central limit theorem to it. And what does it simply say? It simply refers to that if a sample of any population, any sample, if you're randomly sampling from any population, when your n is large enough, the sample size, that means the sampling distribution of your mean, sample mean, would approximately be normal. So that's what it implies. Remember, when you're sampling from a non-normal, from any population, whether be normal or normal, the larger your n, when you have n, when your n is large enough, the sample distribution of your statistic mean, that means of your sample mean, tends to be normal. And you could see the picture down. You could see when you have just few sample size, see how the curve is. When the sample size increases to 2, you see how the curve tends to be curving. It tends to have a curve. Let me use the word curve. And when the sample size is now 10, we look at it forming that normal, giving us that normal curve. And when it's now 25, what do you have? Tends to have the normal curve. So that's what central limit theorem implies, and that's just the properties of it. When you have small sample size, the curve tends to be flat. When n becomes large, it becomes normal distribution. So one practical note we need to know is that from a non-normal distribution is that large sample size are not always attainable, and this could be reasons that sometimes it's cost, and sometimes it's not. You don't need too much sample. For instance, let's look at blood sample. No, so you mustn't draw all the, must use all, we've only drawn all the blood in the system to know our blood group. Is only, we just need little from it. So using the whole population, or using a large sample could be harmful to the system, or could be harmful. So some is not attainable always, and opinion polls have limited sample size due to time and cost of operation. For instance, when you're dealing with people's opinions, availability might be another constraint. The cost implications of the researcher might be a constraint. So it's not always practicable to get a large sample size. And note, not all variables are normally distributed as well. In practical note, income are not normally distributed. Our income varies from one point to the other. So let's take an example of non-normal distribution. This is an example of it when suppose a population has a mean of 8 and standard deviation of 3. Suppose a random sample size of 36 is selected. So what is the probability of that the sample mean is between 7.8 and 8.2? So what we need to do is what we standardize, apply standard, that will standardize the observation. So when you standardize the observation, you have probability now will now be, this standard will give us minus 0.5 and this will give us 0.5. So we're looking for the probability between this minus 0.5 and plus 0.5. So when you check this using the statistical table, you have what? You have, since normal distribution result is symmetric in nature, that means the left hand side is same as what as the right hand side. And when you have that, you see that you check using normal distribution, you have 0.1915 for minus 0.5, between 0.5 and 0, and 0 from 0 to 0.5 you have 0.1915. So when you add this together, we give us 0.3830. And other example you can try on your own is this. I believe you can try this on your own and follow the example earlier highlighted. An important note is also difference of sample means. Suppose we have two sample means drawn from independent populations. So what are their properties? It will interest you to know that if we take the expectation of the difference of the sample mean, will give us what? An unbiased estimate of population, mean of the first population minus mean of the second population. And if you take the variance of the sample mean of the two sample mean difference, it will give us what? The variance of the variance as sigma square 1 over n1 plus sigma square 2 over n2. So that should be noted. And hence we can say for the normal case, we can say the difference of the statistical mean which is normally distributed with the following parameter. That's mu1 minus mu2, comma this, which will replace our, which as shown earlier here. This will give us this. And the same thing for non-normal case. What you need to do is what? We apply central limit theorem. When you apply central limit asymptotically, we assume that what? That means if your n increases, it will definitely be the same. So here for non-normal case, you will need to standardize, or you need to apply central limit theorem, and it will be this. So let's look at it as an example. We look at these examples of students with right hand. The IQ, the mean of the IQ is 80 with variance of 1400. And look at the IQ, the mean IQ of student with left hand student have 80, the same 80 mean and variance of 1320. So we want to find the probability of the IQ of right hand students will be at least 5 units higher than the left hand student. If the sample size of 100 right hand student is drawn and 120 left hand student is drawn, so all the parameter will be taken into consideration. That means 80 variance of the right hand will give 1400 and the mean is 100. When you do the mathematics, Hence we're looking for probability of the variance, the difference of x1, the mean of x1 and the mean of x2 to be greater than 5. So if you apply this, do the mathematics here, we'll have the mean to be, take the difference between the mean, you have 0, and when you do this, you have 25. When you put this in this, you have standardize this, and you have we're looking for probability of z greater than 5, hence you will have 0.1587. So sampling, also we'll look at sampling distribution of sample proportion at the same time. So here we'll look at, instead of looking at the mean, we'll look at proportion. And proportion, as I said, proportion is a fraction of success in n trials. So that means we're looking for possible, if we're looking for the numbers of heads, let's consider a toss of a coin. The probability, the chances of numbers of heads is numbers of x that are success. So numbers of heads in n trial. So let's x be numbers of x in n trial. So that means the proportion of x occurring is what? X over n. That's one by proportion. And we take the expectation. If we apply the central limit theorem to the expectation of your x, so it will give us n pi, and the variance of x will give us n pi into 1 minus pi. And we do the expectation of this, see it will result to be pi. We do the mathematics of this as well, variance of the proportion will give us this. And the same way we can standardize this. When you standardize that, you have that. And the same thing, we can find the sample distribution of different proportion. So that's the same thing applicable to different sample means. You can as well apply this to different proportion. And it interests you to know that the mean will give us P1, expression of the mean. You record the expression of the mean is P1. The variance is what? Is this. And when you do for population 2 as well, you have the same. So when you introduce that into, when you apply your central limit theorem, you realize that you have what? It's your proportion, variance of the proportion with somewhat distributed with what? With mean of this. That this will be your new mu, and this will be our variance. The same applicable, the same central limit theorem is being applicable. So that brings us to the end of sampling and sampling distribution. Please, you can follow us for more. If you have any question, you can follow us and drop your questions. And as well, we urge you to subscribe to our YouTube channel at OA Adejumo. Thank you.